This is the 8th of the videos on the subject of the theory of everything, and I'd like to follow up the last video, the most recent video, on the subject of the energy model, to say something about the calculations involved in that, because they are quite different from Newton's, or appear to be quite different. I don't know how they compare at all with Einstein's general theory of relativity. I don't quite understand how Einstein's theory explains what causes gravity as much as it describes how it works and how to calculate and predict the force of gravity at any given point under any given circumstances. So I can't compare it with him, except to say that I think that the proof that Eddington obtained by studying the lensing of light as it passes the sun, I would have thought any gravity theory should be consistent with that. So I don't think you can say it proves Einstein's theory, although it's consistent with it. Anyway, no more about that. I'm going to talk about the theory that I'm talking about, and I want to just point out that when I said that our equation saying that the total energy equivalent length is equal to the sum of the squares of the separation in space, and this is the 3 dimensions added, and plus, that's a plus sign, plus the additional x dimension, which also can have 3 dimensions. The mass is here, as I've said before, simply to provide a multiplication factor. I'm going to say something later on here on the subject of why our kinetic energy equations have only one mass in them usually. That's an interesting point. I want to point out here that the value of x representing kinetic energy is equal to the period of the system times the rate of change, or times the velocity in space. And the principle of equivalence that I've spoken of before says that the same is true in reverse, that the separation in space is equal to the period multiplied by the rate of change of x, or in other words, the velocity of the body in the x dimension, which is the imaginary additional dimension. So these two are identical, and this represents potential energy, that represents kinetic energy, but the two are equivalent to one another, which makes it even more surprising that we appear to treat kinetic energy as if it were quite different from potential energy. So there's the relationship between the dimensions. Now, our definition for kinetic energy that we use is either the classical one, half the mass of the moving body times the velocity squared, and in the case of Einstein's special theory, the speed of light squared times the increase in the mass of the moving body, and but both of these contain only one mass. And I think that's the reason for that is that we generally are not talking about kinetic energy as it's created by potential energy. We're generally, in our engineering and physics, talking about energy as we create it separately. So that, for example, if I take a ball, I don't have just a large ball, if I push a ball or something and move it along, I'm giving it energy. And it has nothing to do with the potential energy. Pushing the ball along a table on Earth would require the same energy as pushing a ball along the table on the moon or in any other planet, because other than friction, there's no difference between the planets. And that means that the mass of the central body, the body providing gravity, has no effect on kinetic energy. But that's not a natural way of getting velocity. If you were instead to roll a ball down a slope, as indeed some of the ancients did, if you rolled a ball down a slope so that it went down and then traveled along, the kinetic energy here would depend upon the force of gravity, which depends upon the mass of the Earth. So that there is a relationship between the mass of the Earth and the kinetic energy of a body on it, if it's produced by a natural means, not by somebody injecting energy from the outside. And that I'll refer to later perhaps when I talk about Newton's equation. But that, I think, is why it is that we don't include the mass of the Earth in equations for kinetic energy. And the Earth, of course, is so large compared with most moving bodies that we experiment with, so that it requires very, very little reaction energy. If I throw this up, nobody considers the fact that as I push it up, so the Earth goes down and comes back up again. That movement is so small, nobody takes any notice of it. So we ignore the mass of the Earth when talking about the momentum or the kinetic energy of a moving body. So that's the reason, I think. But I have to include it because otherwise there'd be no theory. Now, let me say something more about Newton. You'll notice that my equations make it look as though energy increases as the square of the distance, which is quite different from Newton's equation, which for acceleration, which is mass times the universal gravity constant, g divided by the distance squared. With that theory, the energy increases with distance, but it increases at a reducing amount, and the increase in energy is inversely proportional to the distance, the force proportional to the square of the distance. But the energy, the rate at which energy increases, according to Newton, is inversely as the distance. Mine is that the energy increases as the square and the force increases as the square. But now, why do I say that? Why can I get away with saying something? Well, it's to do with the fact that Newton's equations are not comparisons of the force of gravity on a given body with a constant energy. They are comparisons between different bodies with different orbits and therefore different energies. And so if you compare one orbit with another, you do get an inverse square law. But if you were to take Newton's equation and you could show that the acceleration is also proportional to the distance divided by the square of the period. But the periods of his different orbits are different from one another. So therefore the acceleration can reduce with the radius, but the period gets much longer as orbits get larger. But if you have a body going straight up and down, that body has a constant period. And therefore, if you use that same equation, you can say that the force of gravity is proportional to the height, which is quite different from Newton. And that's where an experiment of sending up a projectile straight up for maybe 100,000 miles and measuring its acceleration would show quite a different, in my theory, would show an entirely different. In fact, if you send it up, I calculated the other day, sent it up at about, say, 18,000 miles an hour, so it came back. If you send it up too fast, it won't come back, according to Newton. But if you sent something vertically at about 18,000 miles an hour, it would go to about the same height above the Earth as the Earth's radius. And according to Newton, the acceleration would drop to a quarter because the distance is twice. My theory says that it wouldn't change at all, and that's kind of interesting. It does, in fact, it is higher at the distance, but according to my theory, when a body is sent up at 18,000 miles an hour on the Earth's surface, it experiences only half the acceleration that a motionless body So there's a big difference in these theories, and it'll be interesting to see if somebody one day proves me utterly wrong, or just possibly perfectly right. Now, that I think is enough for this particular 8th video. I don't think there's anything else I need to discuss right now. So the period, by the way, is very difficult to calculate. It's inversely proportional to the mass of the central body. And I'm working with, right now, with trying to show that Planck's constant might have something to do with it. If you use Newton's general universal gravity constant, then you can show that t squared is equal to the distance cubed divided by the mass and the value of the universal gravity constant. But that assumes that this gravity constant is correct, and I don't like to do that without being quite sure. I'm certainly convinced that I'll put the square in there too, that this is correct. But the rest of it I'm working on to find out how to calculate. I mean, you can measure it and you can estimate it, but in various ways of estimating it. But every way I've tried so far has to assume Newton's theory is correct, and I don't like to base a theory on a theory that I'm questioning. So that'll be enough for the 8th video. Thank you for watching this.